Hey everyone! So in this video I'd like to talk about the distributive law, which gives us another way for computing certain kinds of multiplication. And so before we talk about the distributive law, let's just remind ourselves a little bit about multiplication. So let's say I wanted to evaluate the product 3 times 4 times 5. So order of multiplication doesn't really matter, so we could compute this by multiplying 3 and 4 together first. And what does that look like? Well, that looks like 12 times 5, which comes out to be 60. Or we could actually multiply 4 and 5 together first, and we get the same result, right? So this is 3 times, well, 4 times 5 is 20, and this also comes out to 60. So order of multiplication doesn't matter. Now, let's say I had an expression like this. Let's say we wanted to simplify the expression 3, and then here I've got in parentheses 2a. Well, here, we don't have any operation between these two quantities, 3 and 2a, so this is inferring that there's multiplication, or implying that there's multiplication between these two quantities, right? So this is really the same as 3 times 2a, and 2a is really the same as 2 times a. So this is a lot like the expression we had above, 3 times 4 times 5, but this time we have a instead of the very explicit number 5. But a is there to represent some number, right? So this is really just the same as, I can rewrite this as 3 times 2 times a, which is 6a. Or maybe a slightly different looking example, but very similar examples is 6, and then in parentheses, negative 7b. So this is meant to be a b here, not a 6, by the way. So again, we have multiplication that's occurring here because there's no operation between these two groups, the 6 and the negative 7b. And again, I want to emphasize here that this is a negative 7b. That negative sign is not subtraction, right? So this is telling us that we're going to put together these two quantities through multiplication. This is 6 times negative 7 times b, right? So there's no subtraction involved here at all. And so here this comes out to be 6 times negative 7 is negative 42 times b. Well, I can just leave that b at the end there. Right, so here when we have an expression involving just multiplication, like all of these examples above, well, we can really perform the multiplication in any order we want, and sometimes this will allow us to simplify our expression, rewrite it as an equivalent simpler one, like we've seen here. So now let me motivate the distributive law, which will give us a way to simplify certain kinds of expressions involving both multiplication and addition. And so here I've got this scenario. It says that at a dollar store, all items are $1.10. And NA buys 7 plastic tablecloths and 3 packs of paper plates. And we want to figure out how much NA is going to spend at this dollar store for all of these purchases. Well, there are two different ways we can actually compute this cost, right? So here, let me write that down. So there are two ways to compute the cost. And so, notice that all of the items are $1.10, and NA buys 7 plastic tablecloths and 3 packs of paper plates. Right, so one way I can compute this total cost, the first way that I'd like to discuss, is, well, there's 7 plus 3 total items that are being purchased. And for all of those items, we're going to pay $1.10. NA is going to pay $1.10. So it's going to be $1.10 times however many items there are. So 7 plus 3. And so this will come out to be, well, we've still got this $1.10, and then we've got 10 items here, right? So this is times 7 plus 3 times 10. And then this is equal to, well, any number times 10, I just move that decimal place over 1 unit to the right. This is $11. Okay, well, I said that there's a second way to compute this total cost. Well, every item is $1.10, so we can imagine buying all of the tablecloths first, right? So it's going to be $7, not 7, that's not quite right. It's going to be $1.10 for every single one of these tablecloths, right? So $1.10 times 7 is how much we're paying for the tablecloths. And if we add this with how much we pay for the packs of paper plates, that's $1.10 for each of those 3 paper plates. And we add those 2 costs together, we'll get the total cost. And so this is, well, 7 times $1.10. I know that's $7 plus 7 sets of 10 cents. That's $7.70. And then if I add 3 sets of $1.10, well, that's going to be $3.30. Right, 3 sets of those dollars, 3 sets of those 10 cents, that's $3.30. And then if I add these together, well, 7 plus 3, that's going to give me $10. And then 70 cents plus 30 cents is another $1. So that's 10 plus 1, that's $11. So we get the same result as we expect. But the main point I want to showcase here is not that we can compute this cost and we can do it twice. The main thing I want to emphasize is that really these two ways of computing are the same. So these 2 ideas here, these are the same. They're equivalent ways of computing this total cost. And so this equivalency of how we can compute this cost is called the distributive law. So this equivalence is known as the distributive law. And so what it says is that if we have, an expression kind of like what we have on this left here is that if we have some quantity, maybe I'll call it A, some number, and it's multiplied to a sum, like 7 plus 3, so I'll write this more generally as B plus C. If I have A multiplied with a sum, B plus C, well, we can compute this by, multiplying A with the first term in the sum, so A with B, multiplying A with the second term in the sum, and then adding these together. And so this is called the distributive law because, how are we really computing this multiplication that we see on the left? Well, we're really distributing that multiplication to each term. It's A times the first term, added on with A times the second term. So this is the distributive law. So we can distribute the multiplication across the sum. And so maybe let's see an explicit example of this. We saw one above, but maybe let's just do it again. Let's say I've got 3, and I'm multiplying this with 8 plus 2. Well, how would we do this before when we sort of focused on order of operations? And order of operations always applies. It tells us, let's do the addition in the parentheses first. Well, we've got 3 times 8 plus 2, that's 10, right? So this comes out to be 30, right? And this is without using the distributive law. But what the distributive law is saying is that really this computation can be done another way, an equivalent way. This is really the same as, 3 times 8 added on with, 3 times 2. So this is 3 times 2, which comes out to be 24 plus 6, right? 3 times 8 is 24, 3 times 2 is 6, and adding those together gives us 30. Right, so 24 plus 6 is 30. So we get the same result despite computing this expression, evaluating this expression a slightly different way. And so, another thing I want to mention is that, subtraction can be seen as a special kind of addition, right? So here, subtraction is a special kind of addition, right? It's adding a negative number on instead. And so here, if I see 5 minus 3, right, this is the same as 5 plus negative 3, right? That subtraction is really just a special kind of addition involving negative numbers. And so we can distribute over subtraction as well, right? So if I have something like, let's say, 3 times, here I've got 8 minus 2 instead. Well, normally we would compute this as 3 times 6 using our order of operations telling us to do the parentheses first, and this gives us 18. But I'm saying that we can also, distribute that 3 across the difference, that multiplication across the difference, and we get 3 multiplied with 8, and we're going to add that on with 3 multiplied with negative 2. And so here this gives us, 3 times 8 is 24. 3 times negative 2 is negative 6. And 24 plus negative 6, that's 18. So we get the same result. Distribution applies to differences as well. So the main way the distributive law is actually used is to rewrite or simplify expressions involving variables. And so I've got 3 different examples here where we can apply the distributive law. I definitely encourage you to try these out yourself first if you're feeling ready, but otherwise we'll go over these together. So here, this first example, we've got negative 2 times this difference, 3x minus 1. And so we can distribute that multiplication of negative 2 across this difference. And this will give us, this will be negative 2 times that first term, 3x. Now there's a few different ways we can write this second term that'll end up equivalent, but I'll write it as negative 2 times, or subtracted by 2 times negative 1. And so here this comes out to be negative 6x, and then I've got 2 times negative 1, that's negative 2, and when we're subtracting that, comes out to be positive 2. So you might be able to see this right away and skip that middle step. That's okay too. I personally would myself, but I just figured I'd write it there to be as clear as I can be. But anyways, our final result is negative 6x plus 2, right, coming from that negative 2 times negative 1. Okay, so for this next example, we're going to take 8, and that's going to be distributed across this sum, 6y minus 4. Or not that sum, the difference. And so this is going to give us, 8 times 6y plus 8 times negative 4. And so 8 times 6y, 8 times 6 times y comes out to be 8 times 6 is 48. Then we still have that factor of y. And then we've got plus 8 times negative 4. 8 times negative 4 is negative 32. And adding on negative 32, that's the same as subtracting away 32. And these aren't like terms, so I can't do anything more here. 48 sets of y is very different than 32. I can't just subtract them off as is without knowing the value of y. And then in this last example, here this is kind of rewritten in a slightly different way than we're used to. Here I've got the group that's being added together first, and then I've got the 7 that's being multiplied afterwards, but order of multiplication doesn't matter. This is really the same as 7 times negative 5 plus 4h. And this is the familiar way we can distribute, or the way this expression looks maybe a little bit more familiar for distribution. Or we can multiply that 7 across each term. And so really all this is to show you that here, despite the 7 being on the right side of this parentheses, we can still distribute it the same way we have in the past in the last few examples. And so this is the same as 7 times -5 added on with 7 times 4h. And so this is -35 plus, well, 7 times 4 is 28 sets of h, right? 7 times 4 times h. Well, I can do the 7 times 4 first to get 28 sets of h. And then I can't do anything more here. 35 and 28h, these are not like terms. They can't be combined in any way. So here, this is really the simplest way we can write this expression so that it's really equivalent, describing the same idea as it was above. And so if we tried to subtract that -35 and that 28, we would get nothing sensible. It wouldn't be equivalent. It wouldn't really be describing the same thing, and it would be incorrect. So here, just to emphasize, this is not equal to -7h or -7 plus h or anything like that. We've really got the simplest way we can write this expression right here. So now that we've learned about distribution, I'd like to talk about maybe one misconception that might be floating around. We said in the very beginning of the video that if I have 3 times 4 times 5, well, this is really the same as 3 times 4 times 5. I can do this in any order I want. So I can write this as 12 times 5, for example, and I would get out 60. Now I want to emphasize that the distributive law really only applies to multiplying to a sum or a difference. So here it does not make sense. It would be incorrect to try and distribute 3 across this product here of 4 times 5. Right? So here, writing out 3 times 4 times 3 times 5 wouldn't make sense. You see that we have this extra multiplication of 3 that we didn't have earlier in the example where we compute it correctly. Right? So here, this doesn't make sense, and it also doesn't make sense to write 3 times 4 plus 3 times 5. There's no addition in the first place. Really, there's no distribution we can apply here. And so this is similar when we start looking at expressions. If I have something like 3 times 2x, I can't distribute that 3 with the 2 and the x. This is not the same. This is not equal to 3 times 2 times 3 times x. So that's just one small thing I'd like to emphasize in case you encounter an example like this and your first reaction is maybe distribution. We can only distribute across sums or differences, addition and subtraction. So the last example I'd like to talk about is here I have this expression 5 minus 2 times x minus 3. And I would like to figure out which of the 4 expressions are equivalent to this one. And if you're feeling up for it, definitely try this problem out first. So, how can we tackle this kind of problem? Well, we can try and simplify this expression and see if we come across any of the expressions on the right along the way. And so here, how do we simplify 5 minus 2 times x minus 3? Well, one thing I want to say we can't do is we can't perform the subtraction. Right? Order of operations tells us to do multiplication and division before addition and subtraction. And this 2 is being multiplied with that group x minus 3. So we can't do this 5 minus 2 at all. That'll give us something completely different. And another thing is, we have this group here that we usually perform parentheses. We compute what's inside the parentheses before we do anything else. And so even then that tells us, this is what we should do first. But we can't simplify this x minus 3 without knowing what x is. But one thing we can do is we can perform the distribution, right? This 2 times x minus 3, or this minus 2 times x minus 3, we know how to rewrite that. Right? This is the same as 5, minus 2 times x, and then minus 2 times negative 3. And what I'm doing is I'm taking this negative 2 and I'm distributing it across each term in that difference. And so this comes out to be 5 minus 2x, and then minus 2 times negative 3, well, that's the same as plus 6. And then lastly, we could combine some terms here, which terms, in fact, will, not this 5 and this minus 2x, right? Those are unlike terms. We can't do anything, we can't combine those in any way to get a simpler equivalent expression. Those just are counting different things because of this x variable and the fact that this one doesn't have an x variable. What are like terms are these constants, 5 and 6. So we can add those together to get, well, we have minus 2x plus 11. And so all of these different expressions we see here, they're all equivalent to this original one. So we see here this 5 minus 2x plus 6 right here. That's an equivalent expression to our original expression. Now 5 minus 2x minus 3, that's 3 less than the example above that we know is equivalent, so it can't be the same. Right? So this is not the same, and mainly we can identify that from that minus 3 instead of that plus 6, where everything else is otherwise the same. And so where did that minus 3 come from? Well, here, one common mistake I see is when we try and distribute some quantity across a group of terms that are added or subtracted together, sometimes people forget to really distribute through every term. And so, we can't just multiply that negative 2 with x, we have to distribute it to that negative 3 as well. If you forget it, you end up with an example like this, which is not equivalent. What about the next example, this 3 times x minus 3? Well, what's the difference between that and the one we started with? Well, that's like if you try to perform the subtraction first. If you try to say 5 minus 3 first, and then multiply with x minus 3, that's how we would get c here. But earlier we said that doesn't make sense to do. Right? Doing subtraction before everything else breaks order of operations, and we're not going to get something that means the same thing. And what about this last example? Where does this come from? Well, this is actually the same. This is the same as the expression from part C, right? If we distribute 3, that factor 3 into each term, we get 3x minus 9. And well, we knew C was not equivalent, and so D is not going to be equivalent either.